Hello everyone. In this video we're going to be solving a very interesting polynomial equation. We have x plus 1 squared plus x plus 2 to the third equals 2 minus x plus 3 to the fourth power. Obviously, in its original form, this problem does not look like that, but we're going to add this term to both sides to make it that way. So let's go ahead and add that to both sides, and we're going to get x plus 1 squared plus x plus 2 to the third plus x plus 3 to the fourth equals 2. Awesome. Now, obviously, adding this quantity to both sides is not going to change the domain or the solution set because these are polynomials, so they're all good. Okay, now, I find this equation interesting because notice that the value that we add to x increases by 1, and the powers also increase by 1. So when you add 1 to x, you raise it to the second, and then plus 2 to the third, and then plus 3 to the fourth. Could we continue this and come up with other equations? Probably, but that will be a little complicated. So here's what I'd like to do. And first of all, I want you to take a look at it from a brute force perspective. So whenever you see a problem like this, one of the things that at least one thing you can do is just expand everything and see if you can solve this problem. So let's go ahead and take a look at it from that angle. That's going to be our first method. X plus 1 squared is going to be x squared plus 2x plus 1. This is going to be x cubed plus 3x squared times 2 plus 3x times 4 plus 8. And then plus x plus 3 to the fourth power. I'm going to use the binomial theorem for that. So it's going to be x to the fourth power plus 4 times x cubed times 3 plus 6 times x squared times 9 plus 4 times x times 27. And finally, it's going to be 3 to the fourth, which is 81. And that's equal to 2. Now, let's go ahead and combine like terms, simplify this expression. We're going to be getting x to the fourth as the highest power. So let's start with that. And let's go ahead and combine the x cubed. This is 12x cubed. This is 1x cubed. That's going to give me 13x to the third. And then we do have quite a few x squared. We have 6x squared. We have 54x squared. And we have 1x squared. That's going to give me 61x squared. And then we have x's. This is going to be 108x. This is 12x. And this is 2x. So if you go ahead and add those up, I don't think we have any other x's. 108 plus 12 is going to be 120, 122x. Interesting because 61 times 2 is 122. I don't know if that's going to help us, but it's just a fact. And then we have the 1 plus 8. And then, let's see. 1 plus 8 is 9. 9 plus 81 is just going to be 90. And of course, we have the minus 2 because we have to subtract 2. That's going to give us an 88 on the left-hand side, okay? And we're going to set it equal to 0. Awesome. Well, not that so awesome because this is a quartic equation. There is a quartic formula, but I don't think you want to know it. If you want to look it up, I think there's a nice picture on Wikipedia. It's gigantic. It's ginormous. It's huge. Anyways, the quartic formula doesn't exist, as you hopefully know. If it did exist, it would probably take up a book to write it. Anyways, so this is our quartic. And one of the things you can do is test some rational values. So the rational root theorem tells us, since this is a monic polynomial with leading coefficient 1, you need to check the factors of 88. There's quite a few, like 1, 2, 4, 8, 11, so on and so forth. There's the negatives too. You got to apply. Oh, one of the things that I would like to mention, this polynomial cannot have a positive root. Why? If x is greater than 0, all these terms are going to be positive. There's no sign change. So you're not going to get a 0 from there. By adding positives, you can't get 0. Make sense? So you have to go with the negative values. But that's going to take quite a while to figure out. That's why the first method is not a good idea. Why did I show you that? Because sometimes we use this method and everybody thinks differently. So I guess knowing extra methods would not hurt, would it? Now, here's what I'd like to do. I want to approach this problem, of course, in a smart way. Let's rewrite it. And I think you'll remember how to write it because there seems to be a pattern, right? Awesome. Now, if there are any integer solutions at this point, obviously you can guess and check. That's always possible, and that's going to help you. But let's go ahead and do this. I want to take advantage of some of the terms being canceled out. So for that reason, I want to call the term in the middle y. And don't ask why I picked it. But if x plus 2 is equal to y, this is going to be y minus 1, and this is going to be y plus 1. Do you see what I see? Numbers will cancel out. Hopefully you do. Now we get y minus 1 squared plus y cubed. I don't need parentheses there, right? And then y plus 1 to the 4th power equals 2. Now let's go ahead and expand everything and see what happens. We get y squared minus 2y plus 1 plus y cubed plus y to the 4th plus, again, we're going to use the binomial theorem with 1, 4, 6, 4, 1, but this time it's a little easier. It's going to be 4y cubed plus 6y squared plus 4y, notice the symmetry, plus 1 equals 2. So what's really significant here is that 1 plus 1 equals 2. Duh, right? Everybody knew that. But it just cancels out, leaving us with no constants. That's great. Let's go ahead and combine like terms again. This time it's easier. Y to the 4th power. And then we're going to get y cubed. 4y cubed plus y cubed is going to give me 5y cubed. Plus, how many y squares do I have? 6 and 1. So that's 7y squared. And finally, the y values, 4y minus 2y is going to give me positive 2y. And since there's no constant, I can set it equal to 0. That's what's awesome about this. And then I'm going to go ahead and factor out a y and end up with a cubic inside, which is a lot easier than solving a quartic. And this cubic is somewhat special because it satisfies the rational root theorem. Obviously, this gives us y equals 0, which we're going to explore later. But let's go ahead and focus on the cubic now. So after careful consideration, whatever you want to call it, I realize y equals negative 2 is a solution. Yay, that's awesome, right? And now by using that as a factor, which is y plus 2, I can go ahead and factor my expression as y plus 2 times y squared plus 3y plus 1, and the whole thing is equal to 0. So from here, we're going to find all the y values and then convert them to x values. Remember, y is equal to x plus 2. Don't forget that, right? Y is equal to, well, I forgot it, so I needed a reminder too. Y equals x plus 2, but let's go ahead and solve for y. First of all, y equals 0 is a good solution, and that means x plus 2 is equal to 0 or x equals negative 2. Awesome. Let's go ahead and take a look at the other one. We said that y equals negative 2 is a solution. Y equals negative 2 indicates that x plus 2 is negative 2, and that means x is equal to negative 4. Another integer solution. So if you didn't catch negative 2, you would probably hit negative 4 by using the rational root theorem, right? Hopefully you did. Now, the other solutions are not as nice, but at least they are real, and they have a certain flavor to them. You'll see in a little bit. You probably noticed. But from here, by using the quadratic formula, we're going to get negative 3 plus minus the square root of 5 divided by 2. But remember, this y value is equal to x plus 2. So I'm going to add 2 to both sides, or should I call that 4 over 2, which is going to give me x values. So x from here is going to be negative 1 plus root 5 over 2, right? Because when you add the, when you subtracted the, wait a minute, what am I doing? Okay, I'm supposed to, okay, let's do it this way. Negative 3 plus root 5 over 2 minus 2, that's going to give me negative 3 minus 4, negative 7 plus root 5 over 2, right? That's one of the x values. Or x could be negative 3 minus root 5 over 2 minus 2, and that's going to give me negative 7 minus root 5 over 2. Anyways, hopefully you've seen the golden ratio flavor here somewhat. And those are going to be all my x values. Notice that there are 4 real solutions. Let's go ahead and take a look at the graph and confirm this. And if you look at the graph of these two functions, one of them is a horizontal line, and it intersects the quartic at exactly 4 points. And this brings us to the end of the video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.